Hello guys, welcome to Investigation 2.2. In this investigation, we are interpreting equations for exponential functions. So across the top of your Missing page, you need to write that title down, Investigation 2.2, Interpreting Equations for Exponential Functions. And below that, if you feel so inclined, I told you yesterday that you don't have to write the focus question down, but if you want to write that, the focus question is, how is the growth factor in the initial population for an exponential function represented in an equation that represents the function? So we're talking about representing an exponential function in an equation. So we're focusing primarily on that. So let's begin. Let's look at, first of all, what an exponential function format of an equation is. So an exponential growth equation looks like this. Y is equal to a times b raised to the x power. And looking at this, we have seen in the past for linear equation, we've seen this equation. Y is equal to mx plus b. And if we go through and look at our values, we can see what everything is. The y is that output. Our x is our input, so that means whatever I put into the equation for x, after I do a little bit of math with the slope and the y-intercept, I should be able to find out what the output is. So in other words, I would get a coordinate pair that I could graph on a line, or that I could put on a coordinate grid. I could graph it. Then we also have here m, which is slope. So that's the rise over the run. We're looking at the change in the y values versus the change in the x values, how high it's going up versus how far across, to determine the steepness of our line. And then lastly, we're looking at b, which is also called our y-intercept. So that is where our equation crosses our xy axis, looking at that point right here of intersection. So looking at this whole idea, we are going to identify those same concepts within our exponential function, or similar concepts within our exponential growth equation. First of all, we have an input and an output, and we can probably identify those because they're the exact same variables as our linear equation. Our y is our output. Our x is our input. And what we know about functions is if we put in one thing for x, we'll get one thing out for y. If I were to put in 2 for x into this equation, regardless of what a and b are, if I did a little bit of math, I should only get out one y coordinate. So essentially, I will put in the x value, and I should find out its corresponding y value to plot a point. Doing that, I will be able to identify this as a function, because there's only one x value for every one y value. The next aspect of this is our a value, and that is our initial amount. That is how the book is referring to it. It could also be referred to as our y-intercept. This is where our equation crosses the y-axis. And last, we've already talked about this. We talked about it yesterday. This is our growth factor. This is that constant multiplying of 2, or multiplying by 3, or multiplying by 4 that we're seeing over and over and over and over with our equation. So what I would like you to do is, now that I've written all this down, I would like you to go to your Wordsworth Knowing and write exponential growth equation and add these notes that we have just put here. All of this I want you to add to your Wordsworth Knowing. If you need to, pause the video now. I'm going to move on. So make sure you've paused the video if you want to get all this information. But using this exponential growth equation, we are going to solve a problem. Here is our example problem. We have some scientists. They're studying mold growth on a few burgers from a fast food joint. This is not McDonald's. We know McDonald's doesn't have any mold growing on its burgers, right, guys? Yep, gross. All right, fabulous. So instead, we're going to find the equation for this particular fast food joint, and the scientists have discovered the equation being y is equal to 40 times 3 raised to the d, or raised to d. So our first question that we need to ask ourselves is this. What is the area of mold at the start of the experiment? So the start of the experiment means no days have gone by, nothing has occurred. So if that's the case, D would have to equal 0. So if we had the situation where D equaled 0, we would rewrite this as 40 times 3 raised to the 0 power. Now thinking PEMDAS, order of operations, the bossy triangle, whatever you think of when you're doing order of operations, we need to first pay attention to parentheses and operations within the parentheses. Even though we have a parenthesis here, it's telling us that we need to multiply between 40 and 3. Now that's not the first thing we need to do. Our first thing that we need to do after parentheses would be exponents. This parentheses is not containing an operation within it. So our next step after identifying that there's no operation within a parentheses that we need to do is doing the exponents. So 3 to the 0 power, and if we were to put that into a calculator, we'd find that 3 to the 0 power is equal to 1. So this is equal to 1. We're then going to be multiplying it by 40, so 40 times 1 equals 40. And you're saying right now, Ms. Beardsley, you just told us our initial value or the start of the experiment would be this big, huge yellow number 40 in the first place. Well, now I just proved it to you. Now it's officially 40, and we can all buy the argument that this value of 40, that position of A within our equation right here, that position of A is our initial value, so therefore we can say, what is the area of the mold at the start of the experiment? We can say 40, and I'm going to say this is millimeters cubed. I should have added that on there. Millimeters, actually millimeters squared. Sorry, millimeters squared. Then it also asks us, what is the growth factor? And hopefully now you're getting into the rhythm of things and identifying that the growth factor is that thing that happens multiple times, meaning it's the thing that's multiplied over and over and over, and repeated multiplication equals an exponent value if we wanted to make the shortcut. So 3 times 3 times 3 times 3 times 3, we could rewrite that as potentially 3 to the 5th power, or however many 3's I said. So as of right now, we need to find the growth factor, and if we remember from our previous equation when we were looking at the super general format, our growth factor is this stuff here in blue. So that means the stuff in blue in this particular equation, the reason why it's color-coded is so we can identify it quickly, is this 3. So our growth factor is 3. That means our mold area is tripling each time. That is disgusting. All right, so every day that area of mold triples. Next, what do the variables mean? So we need to identify what each of these variables are. We first have y, which we can say this is our output, but really what does it mean in the context of this situation, in the context of the scientists looking at these burgers and the area of mold growth? We could say the output is the area of mold on the burgers. Gross. The other variable that we have is the D, which in this case we're going to say is days. So each day goes by, the mold area triples. So the D is days. Let's also add, what does 40 mean? 40 is our initial value, which we've already talked about. That means that the area of mold was already 40 millimeters squared when the scientists started the experiment. And the 3 is our growth factor, which means that the mold triples in area. Disgusting. All right, so let's move on. Let's ask another couple of questions. Here are our next questions. What is the area of mold after 5 days? Well, we kind of just lost our equation, so I'm going to rewrite it. Y is equal to 40 times 3 raised to the D. So what is the area of mold after 5 days? So essentially 5 days, we need to rewrite that. I always like to identify what each of my variables are. We're looking for 5, D is going to be equal to 5 in this case, and so we need to figure out what y is. We need to figure out what the area is. We don't know that. So we're going to rewrite our equation. Y is equal to 40 times 3 raised to the 5th power, and do a little bit of math. So first things first, we need to do our exponent. 3 to the 5th power, we can write that as 243. That's just putting it in my calculator, 243, and now we're going to be multiplying it by 40. And so we get the total area of mold growth in 5 days to be y, or the area, is equal to 9,720 millimeters squared. So most likely those burgers are covered in mold. And in all reality, that's a good thing. That means that at one point in time, they were fresh burgers. They were not put in, there was not all sorts of preservatives put in them. It was a good thing. We're not looking at McDonald's. So yes, this is gross, but at the same time, we don't have to worry about these being essentially preserved forever like McDonald's or Burger King burgers. Or any other crazy fast food joint that uses all that sort of stuff. So I need to fix a little bit. We have, on which day will the area of mold reach at least 6,000 millimeters squared? I just added that word, at least. So I'm going to add that in, at least 6,000 millimeters squared. So we're not going to find the exact day, or the exact time of day, but we'll be able to pinpoint that it's maybe on the 7th day or the 8th day. So looking at this information in this equation, if we looked at the information that we had just in the previous question, we were at, in 5 days, we had 9,720 millimeters squared of mold growth. In 4 days, that's essentially taking away, we have taken away an exponent. So if we take away an exponent, another way that we can think of this is we are also going to be essentially dividing by 3, dividing by our growth factor. So if I had divided 9,720 by 3, I end up getting 3,240 millimeters squared. So on which day will the area of mold reach at least 6,000 millimeters squared? We could say between the 4th and 5th days we'll have that scenario of 6,000 millimeters squared being covered on those burgers. So again, while this was a disgusting video, at least we have real life context, right? So let's move back to our initial focus question and see if we've answered it. How is the growth factor in the initial population for an exponential function represented in an equation that represents the function? If we go back and look at our equation of y is equal to a times b to the x power, or our equation that we did, y is equal to 40 times 3 raised to the d, we can see that we have our growth factor represented in our b variable, or that b location, and we can see also that our initial value of 40, or the a, is represented as well in the exponential function. Ideally, that growth factor, we're seeing that it has an exponent tied to it. You have to do that exponent work before you do any sort of other multiplication. So that's the biggest thing that we need to take away from here. I hope this video helps. Enjoy the rest of the day, finish up this investigation, and begin working on the homework. I hope you have a wonderful day. Bye, guys.